We are now shifting gears into the second phase of this course, in which we're going to now start really looking at some organic chemistry and then leading to some biochemistry topics. And so we'll start off with a bunch of different OChem sorts of material. And really the big reason that we have to really study, or a couple reasons really, that we have to look at some organic chemistry. One is that most all the pharmaceuticals that we take for anything are man-made, and they're man-made based on organic chemistry principles. And so what we see here is a fairly large looking type of compound, fairly complicated. We see some things in here that we're familiar with though, such as our lone pairs. And we'll talk about some of this notation, but these are just carbon atoms here at all these vertexes. And so this compound here, we have Synthroid, and honestly, I'm not sure what that is, but some sort of pharmaceutical. And this would be the active ingredient in there. And so it's helpful to sort of know some of the background of some of the basics of organic chemistry when looking at any sort of pharmaceuticals. From organic chemistry topics, we're going to move in the last phase of the course to looking at some various aspects of biochemistry and looking at larger biomolecules such as carbohydrates and things like lipids, DNA, RNA, really large, complex organic compounds. And so really, again, for those, we need to have sort of that a baseline understanding of some basic organic chemistry. And so we're going to start by looking at the very simplest types of organic molecules, just hydrocarbons. As the name implies, a hydrocarbon is made up of only carbon and hydrogen. Carbon is often called the backbone of life because it is such an incredibly versatile compound. Because it has these 4 single electrons around it, it has 4 valence electrons. It means that carbon can achieve its octet by forming 4 different covalent bonds. Makes it incredibly versatile. And so those 4 separate bonds for carbon can be to other carbon atoms, forming long carbon chains, which we'll see. We can be covalently bonded to a hydrogen atom, or to other nonmetals, to other things like nitrogen, oxygen, sulfur, and so forth. And so again, that makes carbon just such an incredibly versatile element that it really is the backbone of all life. And so that's why carbon really has its own branch of chemistry known as organic chemistry. When you hear the phrase organic in referring to chemistry, it doesn't mean that somebody grew it with just cow poop out in their garden. It's not that type of organic. Organic simply means that it's carbon-based, that whatever molecule we're talking about has carbon as its essential backbone. So as I mentioned, hydrocarbons are made up of just carbon and hydrogen. The octet rule always applies, and carbon will always look to form 4 bonds. That could be 4 single bonds, as we see here, with various things attached here on the outsides. We might have 2 single bonds and a double bond. We might have 1 single bond and a triple bond. Or we might have 2 double bonds. That's not as common, but we do see it in some compounds. And so again, just provide some incredible versatility for a carbon atom. When we're looking at things like forces, hydrocarbons, since they're composed of just carbon and hydrogen, there's not enough of an electronegativity difference there to make any carbon-hydrogen bonds polar. So hydrocarbons are completely non-polar compounds. So the only intermolecular forces that exist are dispersion forces, which remember are the weakest intermolecular forces. This means that hydrocarbons have lower melting points and boiling points than compounds that are a similar mass. And we looked at that a little bit before. Remember, we looked a little bit at at methane versus water. Methane, CH4, the simplest of all hydrocarbons. Oh, and I don't even remember what its boiling point is, but methane's natural gas certainly is a gas at room temperature. And so very, very low boiling point. Its boiling point is well below 0 degrees Celsius. Water, on the other hand, molecular weight of 18 compared to the molecular weight of 16 for methane, water has a boiling point of 100 degrees Celsius because there are much stronger intermolecular forces at play. And so hydrocarbons will have very low melting and boiling points compared to polar compounds of similar sizes. Hydrocarbons are typically immiscible, meaning they won't mix with aqueous solutions due to something called the hydrophobic effect. And so this means that for the most part, organic compounds don't tend to mix well with aqueous solutions, with solutions that are made up from water. And so they'll usually separate from each other. You can see that, for instance, with oil and like oil and water. You put together a mixture of oil and water, the oil is going to separate, and that's partially due to density as well, but it's also due to this immiscibility. Gasoline and water will separate from each other because gasoline is composed of various hydrocarbons. We divide hydrocarbons into 4 basic classes: alkanes, alkenes, alkynes, and what we call aromatic hydrocarbons. Alkanes contain only single bonds. They also contain what we call include what we call cycloalkanes, which is a carbon chain then coming and connecting in a ring. Alkenes contain 1 or more double bonds, and alkynes contain 1 or more triple bonds. Aromatic hydrocarbons are unique there are others besides 6 carbon rings, but for our purposes in this class, we're going to focus on 6 carbon rings that have 3 double bonds alternating with each other. So picture actually you don't have to picture it. I should have done this already, but let me go ahead and bring up my whiteboard here. There we go. Okay, sorry for the technical difficulties here. Let's try that again. There we go. Okay. And so the aromatic compounds that we were just talking about, again, for our purposes, going to be these 6-membered carbon rings, and there'd be hydrogens hanging off each of these. I'm not going to bother drawing all those in, but each carbon would have 2 hydrogens. Sorry, for these aromatics, they would each have 1 hydrogen coming off. And we have these alternating single and double bonds. And we'll look more at those a little bit as we go on as well. We have also what we call saturated and unsaturated hydrocarbons. A saturated hydrocarbon contains the maximum number of hydrogens for that carbon chain. And so the general formula for a saturated hydrocarbon would be CN, N being the number of carbons that there are, and H would be equal to 2N plus 2. And so, for instance, if we have 3 carbons, a 3-carbon chain, that would look like this. And remember, carbon's always going to form its octet. And so that would mean we would have hydrogens placed around like so. And so we can see that our formula would be C3, H, 1, 2, 3, 4, 5, 6, 7, 8. And that's our 2N plus 3. And so we have 3 carbons, 2 times 3, or sorry, 2N plus 2. 2 times 3 plus 2 equals 8. And so that's our number of H's. And so this is a saturated hydrocarbon. It has the maximum number of hydrogens that it could possibly have based on our number of carbons. Alkenes, alkynes, or aromatic compounds are unsaturated because they'll always contain fewer than the max number of hydrogens, again, for the length of that carbon chain. So we see a couple examples here, but to maybe draw one out, let's use our 3-carbon example again. Let's say we have a double bond between these 2 carbons. Again, carbon will always form its octet, and so this carbon will have its 3 hydrogens, but this carbon now has 2, 4, 6 electrons around it. So in order to form its octet, there's only going to be one hydrogen coming off that carbon. And this carbon has 2, 4 electrons around it. So to form its octet, it's going to have 2 hydrogens. So now our formula is C3H 1, 2, 3, 4, 5, 6. And so you can see that it does not have the maximum number of hydrogens for that carbon chain, because the maximum number of hydrogens for 3 carbons would be 8. So this is an unsaturated hydrocarbon. And we run into similar situations with alkenes and aromatic compounds. Carbon also, again, since it has an ability to bond up to 4 other carbon atoms, we can find what we call both straight chain and branched hydrocarbons. And so we can see in here, for instance, here's what we would call a straight chain alkane, 1, 2, 3, 4, 5 carbons long. Here's another alkane that's 1, 2, 3, 4, 5 carbons long, but at this carbon, we have another carbon group coming off it. And at this carbon, we have yet another carbon group coming off it. And we'll look into what sort of effect that has both on how we name these compounds, which we'll be spending a lot of time on, and also what that might do to the properties of some compounds. But so we end up with, again, what we call these straight chain or branched chain alkanes. Again, hydrocarbons nonpolar, so they act through dispersion forces. Hydrocarbons that have more carbons will have higher boiling points than hydrocarbons with fewer. And so, for instance, we could have, and I'm not going to draw in all the hydrogens, but we could have a 2 carbon chain versus a 6 carbon chain. And I don't know the boiling points off the top of my head, but this one would definitely be a lower boiling point, and this one would be a higher boiling point. Even though they are just dispersion forces acting on them, there's less surface area for this compound compared to this compound. And so the greater surface area we see with that 6 carbon chain leads to just increased dispersion forces in general. There's just more area for the dispersion forces to act, greater force holding the compounds together, leads us to more energy needed to break them apart, and so higher boiling points. And so if we have straight hydrocarbons, nothing else going on, just carbons and hydrogens, then smaller chains will have lower boiling points, longer chains will have higher boiling points. Straight chain hydrocarbons will also have higher boiling points than branched hydrocarbons of the same size. For instance, for that one, let's say we could have pentane, and we'll talk about this naming, but pentane would be 5 carbons long, again, hydrogens hanging off there in order to form the octets. But so there we've got our pentane. We could also have 5 carbons that were arranged like this. That's still 5 carbons, and in fact, these would have the same exact chemical formula. But this, in the straight chain, is going to be shaped pretty much flat. Again, providing more surface area to act on. As opposed to the one below that, now that's going to form up into kind of a ball type shape. Less surface area to act on, which is going to lead to this compound having higher boiling points and melting points compared to this one. We're going to talk a lot about naming organic compounds. There's a very specific set of rules developed by the same people, the same group that developed the rules that we use to name ionic and covalent compounds, IUPAC, the International Union of Pure and Applied Chemistry. They are the ones that came up with all these different rules. And so if you look up various prescriptions, you'll quite often see things like a generic name or a brand name, Lipitor or minoxidil, something like that. But then there's also the long drawn out chemical name. That long drawn out chemical name is the name that would be derived using our IUPAC rules. There are three basic parts to naming organic compounds, and we're going to use this convention constantly throughout this organic chemistry unit. We have a prefix, we have a root, and we have an ending. Now, I know you can't really see this, but this is the guidelines for some of the naming, which we'll actually talk a little bit more about. No, I don't think we will talk about that later. Sorry, just thinking of what I have coming up in some of my next slides. No, just looking ahead a little bit, we are going to talk more about the naming later. So I'm not going to talk much about the naming now, except really to introduce the root. The root of all the different compounds we're going to talk about in this unit comes down to the number of carbon atoms that are in our main chain. And so this is absolutely a table that you're going to want to memorize. You're going to be using these. And so if there's one carbon long, it's called methane. 2 carbons long, and we'll talk about that ending, that ane, in a little bit. But 2 carbons long gets the root F. 3 carbons long, prop. 4 carbons long, bute, and so on. Some of these should sound a little familiar. Propane, butane, compounds that probably sound familiar to some of you. And so this is definitely a table that you're going to want to memorize. We're going to be using these prefixes constantly. Some of them are probably familiar to you already. Hex, hept, oct are probably ones that you're familiar with. But you will want to know these. This is going to make up the basis of a lot of our naming that we do in the next few lectures. And so that is all for these simple hydrocarbons. In the next video, we're going to go on and look in some more detail at things like naming and some of the more complicated aspects of hydrocarbons. But for now, that's all, folks.